about allocation of mining resources in the blockchain economy. Please.
Good evening, everybody. So my name is Shyam Sridhar, and I'll be presenting our paper, The Allocation of Mining Resources in the Blockchain Economy, on behalf of my talented co-authors, Dr. Stefanos Leonardos and Dr. Georges Piliris from the Singapore University of Technology and Design, and Dr. Yunkin Chung from the Royal Holloway University of London. So before I start, I guess I'd start off by speaking a little more about the motivation behind this project. So it's quite well known that miners are the critical actors in the evolution of permissionless blockchains. And so these miners possess costly resources in the form of, in proof of work blockchains, these costly resources may be in the form of computational power. In proof of stake blockchains, they may be in the form of native cryptocurrency. We also know that the monetary rewards that these miners receive in the form of transaction fees and newly minted coins are in proportion to their individual resources in the network. So keeping all of this in mind, we realize that it is very critical to understand miners' incentive in allocating resources. As from the miners' perspective, efficient resource allocation ensures their profitability. And from the ecosystem's perspective, the reliability of all supported applications depends on the amount and consistency of provided mining resources. So that being said, the objective of our study is to study the incentives of miners to allocate their resources in a single as well as multiple coexisting mineable blockchains or cryptocurrencies. And while doing so, we also take into account the mobility of these resources and the risk diversification of these miners. So the challenge is to test the stability of equilibrium in the case of mining in a single blockchain, and also to find a way to determine equilibrium allocation in the case of multiple blockchains, mining in multiple blockchains. So without further ado, let me go and introduce the math model in our paper. So we first begin by defining a set of miners I, and we assume that the network is consisting of n distinct miners. We assume that the resources that they allocate, or resources that miner I allocates, is xi, which is going to be greater than or equal to 0. In proof of work blockchains, these resources can be in the form of computational power, and in proof of stake, they may be in the form of capital. We also assume the individual per unit cost to be Ci. For example, it can be electricity or amortized hardware costs to produce a terahash per second in the network, or even opportunity cost. In this paper, we've normalized the total network revenue V to be equal to 1. So therefore, we can arrive at this expression for the profit of a miner I in the network who allocates Xi amount of resources. And we can see here, this profit is essentially the ratio of the resources that a miner I allocates divided by the total number of resources that every miner in the network allocates, minus the cost per unit cost associated with allocating these resources Xi by miner I into the resources allocated themselves. Yeah, so this is the profit of each miner. This is the expression of the formula that we can come up with finally. So let's now talk about single blockchain equilibrium. And before moving forward, I would like to formalize the definition of a constant C star. So a constant C star can be defined as the sum of all individual per unit costs for all miners in the network divided by the total number of miners minus 1. And we assume that C star is always going to be greater than Ci for every miner in the network. So this can be thought of as a participation constraint. So essentially, if a miner I has any Ci that is going to be greater than or equal to C star, he shall simply choose not to participate in this game of mining in a single blockchain. So as presented by Arnosti and Weinberg in 2018, we know that the unique pure strategy Nash equilibrium for this mining game at the unique pure strategy Nash equilibrium of mining of this mining game, a miner I which belongs to the network essentially allocates X star, which is equal to 1 minus Ci over C star whole by C star amount of resources. And the total mining resources allocated at equilibrium, that is capital X star, is going to be equal to 1 by C star. So some of the remarks that we can make based on this is that there exist various degrees of revenue dissipation at equilibrium. And also one more interesting remark is the fact that more efficient miners, that are the miners with the lower per unit cost, allocate more resources, therefore increasing his mining share. So the question we pose at this point in time is this Nash equilibrium stable? So a Nash equilibrium may be incentive compatible, but What if a miner wants to increase their relative payoff by deviating from this Nash equilibrium? So we know that coin supply is typically limited. So what essentially matters in such networks is how one is performing in relative terms. To give an example of this, so basically we know that a miner may actually be better off in the long run if they are able to reap 30% of the entire newly minted coins, which would cause them to forgo some temporary profits. And they would be better off doing this rather than trying to maximize or capitalize 20% of the newly minted coins, which would maximize the temporary profits. So what essentially is important is how a miner is performing in relative terms with regards to the rest of the network. And one more question we pose is, can a miner harm others by incurring lower costs to himself? So we know that blockchain networks are actually adversarial in nature. So a miner may be better off by harming others, provided that he himself incurs a lower loss. So at this point in time, we'd like to introduce the notion of griefing factor, which was first put forth by Vitalik Buterin. So the griefing factor is a measure of the utility lost by the network or the victim in comparison to the utility lost by the attacker, or in this case, the deviating miner. So we go on to formalize this notion of griefing factor. So let us assume that X star is the equilibrium allocation. Then suppose a miner I deviates to some allocation Xi, then the griefing factor is just going to be equal to the ratio of the cost incurred to the network divided by the deviator's own cost, which comes out to be this expression right here. So we look at the numerator of this expression. What we are essentially doing is we're summing over various miner j's who are not equal to I in the entire network, and we are basically what we're summing over is the difference in the profit when the entire network is at Nash equilibrium versus when a miner I deviates from Nash equilibrium, whereas the rest of the network continues to mine at this equilibrium. And in the denominator is essentially the deviator's own cost, as we take this difference for that particular miner I. So we can define the griefing factor at X star as a supremum over all possible deviations. So let's look at the griefing factor a little more intuitively. So suppose we say that we start at equilibrium allocation. We move forward with the assumption that a miner deviates to some other allocation. So what we're calculating using the griefing factor is basically the loss or the cost incurred to the network relative to the miner's personal losses. Let's kind of solidify this intuition with the help of an example. So what does the griefing factor of phi mean? The griefing factor of phi essentially means that for a particular deviation, the rest of the miners belonging to the network incur a cost that is 5 times as high as the cost that the deviating miner himself incurs. So if we look at things more intuitively, we know, or we feel that values of griefing factor greater than 1 essentially suggests a threat to the stability. But is it really so? So at this point in time, let's take a short detour and talk about evolutionary stable allocation. So while talking about evolutionary stable allocation or ESA, we always need to look at a homogeneous population. So we assume that miners have the same cost Ci is equal to some constant C for all I belonging to the set containing all miners in the network. So a symmetric allocation X ESA is evolutionarily stable if a miner I deviates from X ESA and allocates some resources X star, while the rest of the network continues to allocate X ESA amount of resources in the network, and the profits of the miners J who continue to allocate X ESA amount of resources in the network will always be greater than the profit of the miner I who's deviating to some allocation X dash. So basically, what we're trying to say is for X ESA to be evolutionarily stable, the profits of the miners that continue to mine at X ESA should always be greater than the profit of any miner I who's going to deviate to some allocation X prime, which is not X ESA. So we know that the unique Nash equilibrium is symmetric, but it is not evolutionarily stable. So a key fact that we'd like to drive home with the help of our paper is the fact that a griefing factor less than 1 and ESA are essentially equivalent. So we know that pi I is equal to pi j for all I and j belonging to the network of the set of all miners in the network for all symmetric profiles x greater than or equal to 0. So we can actually rephrase the previous equation that we had over here by just subtracting pi I x ESA from the left hand side and pi j x ESA from the right hand side. And since they're equal, the inequality does not change. And we also know by definition that pi I x prime and x the profits of a miner I who's allocating some x prime amount of resource which is not equal to x ESA is always going to be lesser than the profits he would reap if he allocated x ESA amount of resources while the rest of the network continues to allocate x ESA amount of resources. So that's what we can do is we can come up with, we can rewrite this inequality as this one right here. So we can say that 1 is greater than pi j x prime x minus I ESA minus pi j x ESA by pi I x prime x minus I ESA minus pi I x ESA. So if we just take a step back and we look at this equation more closely, this is nothing but the individual griefing factor. Why is it so? Because in the numerator, we basically have for any miner j not equal to I, that is any non-deviating miner, the losses or rather the difference in the profits that he gets once the deviation is made, and we find the same difference in the denominator. So essentially what you're doing is you're actually dividing finding the ratio of the loss of some miner j not equal to I when miner I deviates by the same loss of or the same difference of profit or cost incurred by the miner I. So this is not so intuitively based on the concept that we have introduced in the previous slides. This is nothing but the individual griefing factor. For all j not belonging to I, not equal to I belonging to n, and x prime not equal to x ESA is quite important while we talk about this equation. Yeah. So we know that ESA are defined only for homogeneous population. So we've just shown that individual griefing factor less than 1 is equivalent to ESA for such population. We know that network griefing factor less than 1 is sufficient, but not necessary to evolutionary stable allocation. So why not generalize or impose individual or network griefing factor less than 1 to be a stability requirement for any population? So now we know that the Nash equilibrium has griefing factor greater than 1 is a case of overmining. So let's now move on to another theorem that has been introduced in our paper. So suppose we consider the mining game has stabilized at Nash equilibrium for some allocation of resources x star. And if we consider miner I to be deviating with some deviation xi star plus delta for some delta that is greater than 0 for a miner I that belongs to n, then we find that the griefing factor of this strategy xi star plus delta with respect to x star is equivalent to the ratio of the total number of miners minus 1 divided by the product of this deviating factor delta and the sum of all per unit costs for all miners in the network. Let's look at the intuition. So basically we say that, so we can see here that once the network has stabilized at equilibrium, a strategic miner may attack other miners by simply increasing their own mining resources. Now, this may not seem quite intuitive, this may seem quite rather unintuitive, but in reality, this improves the miner's relative payoffs and hence it improves his long-term survival chances. So this is the point that we're trying to drive forward. Some remark that we'd like to say about the previous theorem is a caveat that we have kind of identified that as delta approaches 0, since it is in the denominator of this expression, the griefing factor grows to infinity. However, we'd like to say that the absolute losses for everyone are negligible. So to kind of address this caveat, we have come up with two possible fixes. So the first one is to consider griefing factor in conjunction with the absolute losses. And the second one is to consider discrete deviations, delta, 1, 2, and so on, as it is in reality, But again, it's quite important to take note here that absolute losses do matter. We're still looking at more fixes and trying to come up with a better way to address this caveat, and hopefully we'll be able to do so in the near future. Okay, so this is what Satoshi has to say about all of this. Adding on to the remarks. So with the proportional reward scheme in proof of work mining, the deviating miner basically benefits from overmining because of two main reasons. So number one, overmining increases relative market share. And number two is that more resources imply higher entry barriers for new miners who want to who want to get into this game of mining in a single blockchain. More remarks are that the griefing factor increases with the number of miners. As we can see here in this expression, n minus 1 is in the numerator. So the griefing factor decreases in delta, as we've seen here, since delta is in the denominator of the expression. And yeah, and griefing factor is going to be greater than 1 when we consider only single miners, even when we consider only single miners. Yeah, this is what Satoshi has to say about all of this. Okay, so our key takeaways from what we've observed in mining in a single blockchain or mining a single cryptocurrency can be summarized in this following slide. So we know that for homogeneous miners, the unique Nash equilibrium allocation is not evolutionary stable. Griefing factor less than 1, that is network griefing factor less than 1, is sufficient for evolutionary stable allocation. So if you ask the question, does Nash equilibrium satisfy griefing factor less than 1 in general heterogeneous population? The answer we're going to get is outright no. And we also know from the previous few set of slides that miners are now incentivized to deviate to higher allocations of resources than that predicted by Nash equilibrium. And mining above optimal NE levels, or rather overmining in short, is actually observed in practice, in reality. So yes, you can get better payoffs by spending more money. So this is what we'd like to everyone to take away from the study of mining in a single blockchain or mining a single cryptocurrency. So now let's look at the model of mining in multiple cryptocurrencies. So generalizing the case of mining a single cryptocurrency to mining multiple cryptocurrencies is not trivial for two main reasons. The first one is the mobility of resources may or may not be frictionless. For example, if you consider Bitcoin to Bitcoin Cash, then yes, the mobility of resources is quite frictionless. Or even from a proof of stake one proof of stake blockchain to another proof of stake blockchain. In that case also, yes, the mobility of resources can be frictionless. But what if you consider a case of Bitcoin versus Ethereum? Then we know that there's going to be some friction when you try to move resources from one network to another. And also miners may have different risk profile of preferences. So they may not just be willing to mine the most profitable cryptocurrency at the moment, but they may be willing, or rather they may prefer to diversify their risk. So a way out to this is to introduce a parameters in miners, introduce a parameter in miners utility, which is the constant elasticity of substitution. And so when we do so, we get this expression for the profits of a miner I, as we see in the bottom of the screen. One interesting thing to note here is that if we were to completely ignore the row i's, or as the constant elasticity of substitution, we would see that this expression is essentially the same expression for mining in a single blockchain, except that now it is being summed up to various different coins that a miner has invested in. So the second reason is that then as the network grows larger, the individual strategic influences actually diminish. So do the threats to stability and decentralization that we've discussed in the case of mining in a single blockchain still hold in this case? So one way out is the total network resources xj are actually independent of the miner i's allocation. And one challenge we'd like to bring up here is that common discrete update rules, in particular the gradient descent and best response dynamics, actually lead to chaotic or unstable allocations, even in the case of mining in a single cryptocurrency. Okay, so now let's talk more about the math model. So we basically assume, or rather, we say that mining in multiple blockchains is equal into multiple simultaneous all-pay auctions or dollar contests. Multi-all-pay auctions are actually equivalent to Fisher markets, where the buyers are none other than the miners themselves, and the goods are the coins. And we assume negligible influence here. So proportional response PR dynamics actually converges to market equilibria. And if we consider a case of large number of miners, this market equilibrium is almost equivalent to Nash equilibrium itself. So let's now move on to some of the experiments that we have conducted, taking into account 4 coins, that is Bitcoin, Ethereum, Bitcoin Cash, and Litecoin. So the experiment that we've run here are some of the simulations that we have considered in our study, is that suppose we have 4 coins as mentioned previously, and we have 3 miner types, that is rho. So in our graph, to just kind of explain what exactly these figures mean, so the blue lines here represent the equilibrium allocation, and the red lines represent the proportional profitability ratio, that is PPR. So what is the PPR, or what is proportional profitability ratio? So if you take the example of PPR of Bitcoin, it is essentially the revenue of Bitcoin divided by the cost of Bitcoin, and this ratio is divided by the same ratio, or rather the sum of this ratio for all different coins. And in this case, the coins are Bitcoin, Bitcoin Cash, Ethereum, and Litecoin. So the PPR can be calculated only from observable data. So over here, so we consider 3 different values of rho, that is rho 0.1, rho 0.5, and rho 1. So rho 0.1 basically means no mobility or complete risk aversion. And rho 1 basically is a strategy of selecting the maximum PPR, so the coin that gives the maximum PPR, and allocating all your resources there. And rho is equal to 0.5 is actually somewhat of a middle ground between these 2 extreme edge cases. So what we interestingly observe here is that for the 2 extreme cases of rho is equal to 0.1 and rho is equal to 1, we see that what we calculate in theory, or what we assume to observe in theory, actually significantly departs from the actual observed behavior. So you can see here in the first row and the last row for the 4 different coins, you can see that there is almost no correlation between the blue lines and the red lines. So there's no they don't coincide anyway, and there's a significant difference between what the proportional response dynamics kind of predicts and what is actually observed in reality. But what is interesting is that if we take the case of rho is equal to 0.5, which is somewhat of a middle ground of these 2 extreme cases, we see that the equilibrium allocation and the proportional profitability ratio perfectly coincide. We thought this is quite interesting, and so we can actually find out the equilibrium allocation from the PPR itself. So with that, I would like to conclude my talk, and I would like to thank all of you for your patience.
Thank you. I really like the concept of the relative utility. Just one quick question, then we can talk more during Q&A. So you mentioned for generalizing the result from single blockchain to multiple blockchain, of course, the moving in between the blockchains are not frictionless. That causes difficulty. Assume for a moment that there are several blockchains. They are really the same architecture, and you can really switch between them frictionlessly. Will that make the generalization easier? Can you say something about that?
So yes, this actually makes this generalization easier as the value of rho increases.
So the same conclusion about the graphing factor would be can also apply there.
Yes, that would be. Yeah. That would be correct. And so exactly what we're doing through this constant elasticity of substitution is that we kind of capture the mobility of resources and risk aversion. So yes, so the answer, in short, the answer to the question is yes.
Great. Thanks. If you stay at the Q&A, we can continue the discussion there.
Okay, thank you very much.